Hi, I'm Dr. J, and this is a video about binomial random variables. This is a video part 4 of a 5-part video series all about discrete random variables. The previous video was part 3 and it talked about Bernoulli random variables, and binomial random variables will be an extension of Bernoulli random variables. So, binomial random variables, if we think about having an IID sequence of Bernoulli random variables, as we discussed in that previous video, and then we think about just adding those up, right? So we have these binary random variables, Bernoulli random variables. They're 0 or 1. 1 if it's a success, a 0 if it's a failure. And if we just add those 1s and 0s up, then what we have is a value y. And that value y is the total number of successes in that overall experiment that we did, or that sequence or set of experiments. Because each individual experiment is random, so that is each of the individual xi's are random, the sum of those random variables that we're calling y here, that will also be random. All right, there will be two parameters for a binomial random variable, just like there was a single parameter for a Bernoulli random variable. That parameter was p, the probability of success. For a binomial random variable, there will be two parameters, and they will be p, the probability of success in each of the individual experiments. Since they are IID, they are identically distributed, which means they all have the same probability of success p. And then the second parameter will be n, the total number of trials in our binomial experiments. That is, how many of these individual Bernoulli experiments did we perform? All right, so y is just the total number of successes. The two parameters here are n, the number of attempts, and p, the probability of success. All right, the probability mass function, we can sort of intuitively, there's a more formal way to do this, but we can intuitively get the probability mass function for a binomial random variable to think about the probability mass function for a Bernoulli random variable. All right, so if we think about so first off, let's think about the support for this random variable. So the support are all integers 0 up to n. That is, in our experiment, our set of Bernoulli experiments, again, what I typically think of here is flipping a coin. So when we're flipping that coin, and we're saying, well, if we flipped it n times, however many n is, how many heads could we get? Well, it could happen that every single one of our flips were tails, in which case we'd get 0 heads, right? And it could happen that every single one of our flips was a head, in which case we would have n heads, right? And it turns out that any integer in between 0 and n is also possible. So the support for binomial random variable are the integers 0 up to n, where again n is the total number of attempts of that particular Bernoulli experiment. All right, so what we can start with is to think about, all right, so imagine that we got, out of our n attempts, we obtained y heads, right? Y is some number, right, in this sample space for the experiment, some number 0 up to n. So that's y. Then n minus y is the number of tails or number of failures we got in that series of experiments. And for each individual coin flip, right, the probability of getting a heads is p, and the probability of getting a tails is 1 minus p. Or said another way, probably getting a success is p, a failure is 1 minus p. And so when we go to think about for a particular sequence of heads and tails, right, we have y heads and n minus y tails, then we're going to have p to the y, right? So we're going to have p y's, so multiply p times p times p times p for all of the successes, right? We do that y times because we have y successes. Then we're going to have 1 minus p times 1 minus p times 1 minus p for all of the failures, and there are n minus y failures. So for particular realization of an experiment with y heads and n minus y tails, I keep saying heads and tails. I should really be saying success and failures. For y successes and n minus y failures, the probability of that particular sequence is p raised to the y power times 1 minus p raised to the n minus y power. But now it turns out that most of the experiments could happen many ways. That is, the number of successes could happen many ways. Obviously not if you have all successes. If you have all successes, that can only happen one way, and that is getting all successes, right? But if you had, say, an experiment where you did 10 trials and you got 3 heads, 3 successes, then it could have been the first 3, or it could have been the first, second, fourth, or it could have been the 3rd, 5th, and 10th trial, right? And so we need to account for the fact that it can happen many different ways to get 3 heads or 3 successes out of 10 attempts. And so there's something called the binomial formula. It's right here. So for n attempts and y successes, the number of different ways that can possibly happen is n factorial divided by y factorial times n minus y factorial. So it turns out if we multiply these two pieces, then we get the probability mass function for binomial random variable. So there it is. So it's n choose y. Maybe I should have said that. This binomial formula is typically read as n choose y, right? So that's the one with the parentheses around it. N choose y times p to the y times 1 minus p to the n minus y. And that has a support of values 0 up to n, the integers 0 up to n. All right, so that's the probability mass function for a binomial random variable. From that, we can derive the expected value. And now I want to pause the video, or actually I want you to pause the video and derive the expected value for this binomial random variable. And I've given you a hint here. The hint is that you should go back to when we talked about the properties of expectations. That slide that talked about the video, that was part 2, that talked about the properties of expectations, will be very helpful right here in deriving the expected value for a binomial random variable, which is the sum of independent and identically distributed Bernoulli random variables. Alright, so here's the pause. Okay, so let's just do it. So it turns out when we take the expectations of that sum, then because of properties of expectations, we can reverse the expectation and the sum. So we have that's equal to the sum of the expectation of each of the individual Bernoulli random variables. On part 3 of the slide set, we derived the expectation for a Bernoulli random variable, and it was p, and they are identically distributed, so they all have this expectation. So that's p. Then we're going to sum that p n times, and so we have a total expectation for a binomial random variable that is n times p, or np. Alright, so now let's move on to variances. Oh, I gave you the example, or gave you the answer. Right now, you should pause the video and try to determine the variance for this binomial random variable y. And similar to expectations, if you go back to the slide to determine, to look at the properties of variances for independent random variables, that will help. So here's the pause. Okay, so the variance here for a binomial random variable, where that random variable is the sum of IID Bernoulli random variables, we can, similar to the expectation, we can swap that variance and the sum. So we have that the variance of the variance of the binomial is equal to the sum of the variance of the individual Bernoulli random variables. Each of those individual Bernoulli random variables has a variance of p times 1 minus p. We take the sum n times over that quantity and we get np times 1 minus p. Alright. So that's good. That's the properties of binomial random variables. The last thing I want to talk about is the cumulative distribution function. As a reminder, the cumulative distribution function is just the probability of being less than or equal to some number. And so here, there's really nothing fancy about this formula, although maybe it looks kind of fancy. Basically, all we have to do to find this is we have to sum up each of the individual values in the probability mass function up to the value we're interested in. Okay. There's a little bit of funky symbol on top of that summation sign. That symbol is the floor of y. That is basically just the round down function. So if you want to take, for instance, the cumulative distribution function at 5.5, right, you have to round down to 5, and then you can take that sum. All right. So let's just give an example. So we have a box here. That box has 15 components. We know from prior experience that the failure rate for each individual component is 5%, and we're going to assume that they're independent of each other. Okay. So we can calculate probabilities like this. What's the probability that exactly 2 out of the 15 components are defective? How about the next question? What's the probability that at most 2 components are defective? Or more than 3 components are defective? Or more than 1 but less than 3 are defective? More than 1 but less than 4 are defective, which really means 2 or 3, okay? All right, so we can use the probability mass function and the cumulative distribution function to answer these questions. And so it will look like something like this, but again, you might want to pause the video and try to write down what you think the answer is going to be, how you would do the calculation. You should go ahead and do the calculation and make sure that it actually works out. So here, what we need to do for this component situation, because we've assumed that each of these components are independent, each of them have the same probability of being defective, therefore the total number in the box of 15 components that are defective is a binomial random variable with 15 attempts and a probability of failure here, right, of 0.05. So this is where I mentioned before when we talked about Bernoulli random variables, the determination of success versus failure is arbitrary, so you can define it either way. So the probability of being defective is 0.05, so y therefore is the number in the box that are defective. Okay. All right, so if we're interested in what's the probability that they're exactly 2 defective, we just have to evaluate the probability mass function at that quantity. And so that's just plugging in numbers, n equals 15 and y equals 2 and p equals 0.05 into that equation, and we would get an answer, which I don't show here yet. Okay. All right, if we want what's the probability it's less than or equal to 2, right? Well, that's just a sum over the values less than or equal to 2. So sum 0 and 1 and 2, where we evaluate the probability mass function under those different values, 0, 1, and 2. If we're interested in what's the probability it's greater than 3, all right, well, there's 2 ways you could do this. The easier way, because it involves less elements in the sum, is to say, well, the probability being greater than 3 is 1 minus the probability of being less than or equal to 3. And that probability being less than or equal to 3 is just the cumulative distribution function. It just means we sum up the values in the probability mass function that are less than or equal to 3. So now our summation goes from 0 up to 3. And we evaluate that probability mass function at each of those values. The last one was, what's the probability that it's between 1 and 4? Well, that's the same as the probability of being 2 plus the probability of being 3. And that's the sum that's given here. All right, now my recommendation is not to ever do this by hand. Instead, let's let software do it for us. In fact, you should let me know, perhaps in the comments. Let me know if you tried to calculate this by hand and see how often you got it right? Or did you often make typos, right, that led to an incorrect answer? My guess is that you often did typos that led to an incorrect answer. So instead, we're going to let software do the hard work for us, and we're going to learn how to do the calculations in the software. So here's an example of doing the calculations. This happens to be in R. So in R, we can set up that n is equal to 15, that p is equal to 0.05, and now we have a binomial random variable with n and p. There are a number of different functions that we can use to calculate quantities that we need. So I just wanted to illustrate here that there is a choose function in R that can give you that binomial coefficient if you're interested in it. And so that's just the first example. But after that, we start answering the questions that were posed on the previous 2 slides. So the first question was, what's the probability that you have exactly 2 failures? Well, that's evaluating the probability mass function of a binomial random variable. It turns out in R that function is the D binom function. That D will make more sense when we get to continuous random variables than it does right now. All right, so D binom, we'll do that calculation. What's the probability it's exactly equal to 2? And what do we get? We get about 13% or 0.13. If we want to evaluate the cumulative distribution function, the function we need in R for that is the P binom. Right? P again, when it's cumulative distribution function, right? You just gotta remember these, or you can look at the help function, which you get to in R by typing question mark the function name, say D binom, and it will tell you what the different functions are. So P binom is the CDF or cumulative distribution function. That second question said, what's the probability there were 2 or fewer defective components? And so we just do P binom of 2 with n and p, and that tells us the probability is, I can't even read it, it's so small, is 0.96, right? So 96% chance that there are 2 or fewer defectives in that box. The next one was, what's the probability we have more than 3? Again, we don't have a function that directly calculates that, so we'll calculate 1 minus the probability that it's less than or equal to 3. And so we use, again, that cumulative distribution function. We do 1 minus p binom of 3 at n and p, and that tells us, well, it's something pretty small. I think that's 0.005. All right, the last question was, what's the probability that there are between 1 and 4 exclusive defective components. And so there are two possible ways to do this. One that's shown here is just to calculate the probability mass function of the two, and we just sum them. The second one would be to calculate two different CDF values and subtract them. So I'll leave that to you guys to figure out. Alright, so that's the last slide in the binomial random variable video. The next video will be on Poisson random variables. Hope to catch you there.